Okay, guys, we're going to get into Bohr diagrams, which are the beginning of something more complicated called electron configuration. So to start off with, let's look at the Bohr diagram of boron. Okay, so boron, it is element B, and it has 5 electrons. We know that because its atomic number is 5. If we were to look at this Bohr diagram, this would be the nucleus. This would be the first ring, which is the same as energy level, and this is the second ring or energy level. We know that it has 2 rings because it is in the second row of the periodic table, moving left to right. It is in the second row, second period, so it's going to have 2 energy levels. All right, so next piece is where those 5 electrons go. They're going to start filling closest to the nucleus. I'm not going to put dots, I'm just going to put slashes instead. It's easier for students to see. So the first 2 electrons go on that first ring, and then the second 3 electrons go on the second ring. Okay, so it has a total of 5 electrons, 2 on the first ring, 3 on the second ring. To make this a little bit clearer for you, I'm going to color the electrons on the first ring with this orange, and the electrons on the second ring with this kind of purple. Okay, so this is our typical Bohr diagram, and we would say that the first ring, the first level, has 2 electrons, and the second ring or shell or energy level has 3 electrons. All right, now let's imagine that we zoomed in on these rings so that we could see them very, very close up. And when we looked, I'm going to take a kind of a slice out of this to make it a little bit easier. But when we look at this first ring, we can still see it has 2 electrons, and we have the second ring, and it has 3 electrons. This is called sometimes a pie slice model, okay? And it's called a pie slice model because it's kind of like taking a slice out of the pie. It allows us to be able to zoom in a little bit better, okay? But if we zoom in even more and even closer, we find out that this first ring is just 1 ring, but the second ring is actually 2 rings very close together. So the first ring has 2 electrons, but it turns out that the second ring is actually 2. The first one has 2, the second one has 1. Notice that these are still the same electrons. We're just zooming in more and more and more, okay? And if you want to think about it this way, you could think about this as being thicker, and as we zoom in, we can take it apart. So, N stands for energy level, and the first ring had energy level 1. The second ring had energy level 2. But within that energy level, there are sublevels. The first sublevel in any ring is always called S. The reason why isn't important, it's based on German, okay? The second energy level is P. It turns out that each energy level has a maximum number of electrons, and the first sublevel has a maximum of 2, no matter what level it is, and the second sublevel has a maximum of 6. Now, most of you have probably peeped out at this point that this first ring holds 2 and the second ring holds 8. Notice that 2 plus 6 is 8. Now, if we were to continue, which we don't really have to draw them, there's a third energy level, and that third energy level could be broken up into S, P, and D. And for the sake of just our discussion, we'll make that a different color. This first one holds 2, the second one holds 6, the third one, the D, holds 10. There's a S, a P, a D, a F. We'll talk about F on another day. But what I do want you to know is that the second ring holds a maximum of 18 electrons. Okay? Now, some of you have learned 288, but that was because your teacher was teaching you a shortcut. The real truth is it's 2, 8, 18. And if you look at the periodic table, the first row has 2, the second row has 8, the third row has 18, and we'll talk more about that later. Now, here's what's really important about this setup with the boron. With boron, it's difficult to draw all of this out this way. It's hard to communicate that, and so it's easier to write it in shorthand. And the shorthand that we write, we would call it an electron configuration. So the electron configuration for boron looks like this. The symbol with the number of electrons inside brackets, it's equal to 1s2, 2s2, 2p1. Notice that this number that looks like the exponent is the number of electrons on that ring. And this is the number of electrons on this ring. And if you add all the exponents up, 2 plus 2 plus 1 should equal the 5 on the other side. Now, this looks weird, but it's really not that hard. I promise you, this is one of the easiest things that we do all year, and it kind of scares people sometimes, but it's really super easy, okay? I'm going to show you one other little piece of information. Nope, we'll hold off on it. Let me do one more problem for you, and then your assignment is going to be to do the odd pie slices. I want you to do the pie slice and the electron configuration for the elements 1 through 18, every other odd. Okay, so that means you'll do number 1, you'll skip 1, you'll skip 3, then you'll do 5. I just did 5 for you. Then you'll skip 7, you'll do 9, you'll skip 11, you'll do 13, you'll skip 15, and you'll do 17. Okay, so this is your homework. Well, it's really more classwork, but these are the pie slices. So when I say I want to see pie slice number 1, this is what I'm talking about. Now, a couple other key things that I want you to see is the number of valence electrons. Your number of valence electrons here is 3. Your valence electrons are always your outermost S and P. You'll never count D's. So you're looking at the outermost here, S and P. Your core electrons is going to be 2. Okay? That's all the other electrons. All right, so I will post a whole separate post to show you another problem. Okay, I want to show you one last thing, and that's something we call the noble gas configuration. The noble gas configuration uses the largest noble gas at the end of the previous row. The noble gas at the end of the previous row. So if you're looking at a periodic table, which conveniently, as I am trying to find one, I don't have one handy. If you're looking at the noble gases, it's always going to be the one at the end of the previous row. So in our case, it's going to be helium. So boron is here. The end of the previous row is helium. If I was doing aluminum, it would be neon. If I was doing vanadium, it would be argon. If I was doing magnesium, it would be neon. It's always the one at the end of the previous row. And it happens to also be the one that is all of your core, the same electron configuration as your core. So it turns out that if I look at helium, helium has an electron configuration of 1s2. Use the wrong reddish color. Okay. So if I was wanting to write this short, instead of writing the whole thing for boron, I could write helium 2 and then all this other stuff. Now, that doesn't seem like a real shortcut at this point, but when you get further and further and further and further down, it becomes a great help in order to shorten things. So a good example would be, for instance, potassium is 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, and I could just write argon 18 for S1 for its noble gas configuration. So as you keep going, because by the way, all of this is argon, it becomes a better help. We'll talk more about this later. Just remember, your classwork is to do the pie slices for 1, 5, 9, 13, and 17. And for each of these, I want the pie slice fully labeled like this. I want the electron configuration, the number of valence and core, the noble gas configuration. And that's it.